Yeah.
You need to make it go
That's something to
box
because it is.
to start the slideshow or something.
If you can.
Don't you need to make it go full screen like starting the slideshow or something?
It's
You can do that down there.
That's one. But you. So it's just so maybe I can change one. Yeah, the house is yeah, and then
Can you all see it? Is it still shared?
what's is you would make a contact with the
Anybody out there in Zoom land? Can you see that?
country. And you would be like
Is it being shared?
impression that I made. He
I see a diagram, extra class license, element 4.
confirm it right there within my community. You can see he's got you recorded as a.
So we're talking about diodes.
Okay.
And
You know you're not asking for anything because right. It's changed.
We got these in other people here.
It starts from that question.
Talk about a waterfall, but waterfall being on display.
well,
This
that's
Right,
right.
like
All right.
FTA. FTA.
What's the failure mechanism when a junction diode failed due to excessive current? Well, I guess there's a whole chart missing about junction temperature. It was there
Yeah.
a day or two ago.
I do.
Watch the next slide, maybe revert the slides.
But anyway, the answer is excessive junction temperature. As the current through the junction goes up, so does the temperature. And the semiconductor devices can only tolerate things up to a certain temperature. And then they sort of break, go volcanic.
So the question is the last slide before takeaways. So the answer got to the front of the stack.
Okay. Actually, this should probably be the first one. So we're talking about diodes, the different types. Talk a little bit about Zeners. I mentioned varactors, pins. So it's a two-terminal device, anode and cathode. Even when it's a tube, a vacuum tube, which was the first diode. It conducts in only one direction, and they've got, you know, at least a dozen different types, maybe more, by different fabrication techniques and playing games with type of semiconductor material. Standard symbols that you'll see for a normal diode is just a triangle with a bar representing the cathode. And they're usually marked with a stripe on the cathode end for most of the least smaller ones. We have Zener diodes, and it has this sort of Z as the cathode, representing the Zener effect. And that means that it will conduct current in the reverse direction at a specific voltage. We have Schottky diodes, where that's supposed to look more like an S. This guy named Schottky invented it. Varactor diodes, where they make use of the varying depletion region to make it a voltage variable capacitor or reverse bias. Tunnel diodes, I can't say a lot about, other than you need to know the name. There's light emitting diodes, and we represent it with a couple little lines showing the light coming out, as opposed to a photodiode, where we have arrows showing light coming in. Turns out all diodes emit light, and all diodes are photodiodes. Some are just better than others. If you are actually could take the cover off of the diode and expose the junction, you would be able to detect light when you pass current. Now, The light emitting diodes, they change the material so it emits more light and they control the color. But it turns out when the electron at a high energy, when it's free, goes into a hole, gives off that energy. And that energy is in the form of photons and phonons. You've probably heard of photons, that makes light, or whether it's visible or not. Phonons are lower frequency energy, which causes vibrations or heat. So that's where the heat dissipation comes from. Okay, so here we're back to our P-type material, where we've got a hole. We've got N-type material, where we've got an excess electron in the crystal. And we have what's called intrinsic type, which is pure silicon. And that comes up for a pin diode. I never knew what a pin diode was. No, I did this. So the p-n junction, we saw this same chart before, so no difference. The depletion region, the two materials conducts in one direction, has a built-in potential difference of 0.3 to 0.7 volts. Some of these other diodes, actually, I think can get below 0.3, the material. So first one is the Zener. Allows current to flow in both directions. When it's forward biased, it obeys the silicon threshold. When it's in reverse direction, it conducts at the Zener voltage, which they manipulate with the type of material. Once it conducts, it has very low resistance, so it's essentially a constant voltage drop across it, which is why it makes a little voltage regulator circuit or a voltage reference. And you probably see more of them using the voltage reference, where it doesn't have to supply hardly any current, but it makes it a very stable voltage source. This shows the symbols. The American symbol is pretty much always this. This might be European, I don't know. I've never seen one with part of the Zener missing. The plot shows the conduction in the forward and in reverse. So when it Zeners, it's just basically avalanches. You can see it's almost parallel, so there's very low series resistance. So what's the most useful characteristic of the Zener diode? Right. Varactor diodes. This is where we use the depletion region. And the fact that when you reverse bias the diode, and you can do this with any diode, it's just that they manufacture Varactor diodes slightly different to enhance the effect. But by varying the reverse bias on it, you can control the width of the depletion region, which is essentially making a capacitor between the two terminals of the diode. And I think that's basically the only thing used nowadays as a voltage controlled tuning circuit. Where in the old days you had a capacitor with plates that intermeshed and you rotated it to control the capacitance.
Was that the type of diode they would use in the tuning of magnet?
No, they use the ones with the plates.
Okay.
Yeah, the vacuum ones are I don't know, are they tubular? One goes inside the other, or are they plate?
No idea.
The ones that I've seen are plates.
Okay.
And it's almost like a half moon on each side.
Yep.
And the more they match up, it changes.
Okay. I've only seen pictures and not the inside.
When I went through school, back in the 80s for Navy, it was called Variac.
Okay.
They still have the same name.
Not to be confused with the Variac that varies AC voltage. Okay, so this is showing the construction of a varactor diode. Where they have the metal contact and you got your P-N junction. And they have a N plus junction, which I think is, they do with more free electrons. But they dope it differently. So you can, the other side is showing the width of the depletion region versus the reverse bias voltage. So the lower the voltage, the higher the capacitance. And they don't vary by great amount. They're in, picofarad range.
Now, that's what I was gonna say, because the reason we use larger capacitors, with a component, you're not gonna vary that width very much. Like a depletion region, you're not gonna change the overall capacitance very much.
Well, and that's why for a transistor, for instance, that the base emitter is going to have, 5, 10 picofarads of capacitance, which is that depletion region.
Right.
Okay, so what type of semiconductor device is designed for use as a voltage controlled capacitor?
What we were just talking about.
That's a hard one. Maybe you get that one. Pin diodes. I don't know much about pin diodes because I've never done microwave stuff. But they claim it can operate as a variable resistor, and they're constructed different than a regular diode. And they can also be used as an RF switch because you are essentially controlling the resistance from a high to a low. You can switch it. They have very low junction capacitance, which makes them more usable at very high frequencies. And the forward bias current is used to control the attenuation or the effective resistance of it. Says the resistance is inversely proportional to the DC bias current. And they're in the 0.1 to 10K range, which is pretty wide.
Pin diodes is what they use like for switching, for a radio switching an external amplifier. It's much quicker than the relay and those types of things that they.
And they use it in a multi-band to switch bandpass filters.
Okay.
There's a symbol for a pin diode, and it's different because it's got a line going all the way through it. And this is where the I material comes in, or intrinsic, which is essentially pure silicon. Don't ask me how the physics of this one works. You don't have to know. What's the characteristic of a pin diode that makes it useful as an RF switch? See? Low junction capacities. If, let's see. If we can get that. I guess it's because of, relatively narrow. So the area between these two is going to control the part of the capacitance. There's the effective dielectric, and the area of the plates is what determines the capacitance. So they make these where they're very small, and they won't conduct a lot of current, but they don't have to act as a switch.
So do they handle high current? Or they just use to signal to do the switching, and then there's another circuit that handles the higher current if you need
I
it.
believe. But like I said, I've never used one, so I don't know a whole lot about them.
I've only heard it mentioned.
So
You're using a small voltage to control a very
Well, you're controlling a resistance. Think of it as a voltage controlled resistance. So you're switching a high value resistance in series with something or a
You
low.
control it with a very low voltage that has the capacity to add resistance in a very high voltage circuit.
So what is used to control attenuation of RF signals by a N diode? Or bias current that controls the effective resistance or attenuation. It was inversely proportional. Okay, we got Schottky diodes, named after Walter Schottky. They used to call them Schottky barrier diodes or hot carrier diodes. And it's different in that it's a junction of one of the semiconductor materials with metal, as opposed to a normal p-n junction. They have very low forward voltage drop, okay, 0.15 to 0.45 volts. So it's lower than, a lot of cases, lower than germanium. They're very fast switching action because they're low capacitance also. And because of the low voltage drop, it's faster to get across the junction. Okay, build up enough energy to cross it. They use them as mixers for VHF, UHF because of the low forward voltage drop. We're going to ring mixer circuit with diodes because they're not perfect diodes and the voltage drop across them when they conduct. You get some distortion of the waveform. So the closer that is to zero, the better it is, and the faster they can detect or mix a high frequency signal. When they put them in digital integrated circuits or logic circuits, there was a whole family of TTL based on Schottky. They were much faster. And then they came out with low power Schottky. And then finally they came out with CMOS. So the Schottky and then the low power Schottky, which was almost as fast, switched much faster than normal TTL logic. So it's made with some metal surface plating, I think. Actually, here it looks like a little blob or something. Can you say what that metal is? Gold leaf.
It's the contact is gold leaf. It says.
Basically, it's a metal to N-type silicon interface. So that's where it doesn't have that same barrier junction. And the symbol is kind of sort of the German S, half of a swastika. So what's the important characteristic of a Schottky diode compared to an ordinary silicon diode when used as a power supply rectifier?
Less drop.
All right. And less power dissipation for the same current. Which of the following is a common use of a Schottky diode?
No. VHF, UHF.
It says that's been withdrawn.
It said what?
This question has been withdrawn.
Oh, really?
E6B Diodes. Yep.
Oh, good. You don't have to know it. What's the answer anyway?
It doesn't say.
Well, it's yeah, I'm like
UHF mixer.
Never mind. Very quick.
I don't know
Check
if,
the revision date on your book.
I don't know if Dan missed that or, I did. Cause it's in his book.
No, I don't have the name, but.
There was an errata sheet that came with that.
Yeah. But it's still in the printing, whatever. You won't miss it because it won't be on there, but you know it. So which of the following is a Schottky barrier diodes?
Okay, no. No,
It's a metal semiconductor junction.
no.
Right.
Yep.
It's a weird one. One of the weird ones. The tin diode is kind of weird because it's a PIN junction.
It's the golden dome.
Point contact diodes. I'm not familiar with these either.
Cat whisker, yeah.
Except when I built a radio with a razor blade and a safety pin with the oxide on it, basically this is what you're making.
Okay, MacGyver.
You didn't build one of those when you were a kid?
I did not.
Toilet paper roll with wire wrapped around it, razor blade, safety.
I was too busy blowing stuff up with Christmas balls.
So, it's an N-type substrate and a tungsten or phosphor bronze wire called a cat whisker. It has extremely low junction capacitance because its interface here is that wire. So it has very small cross-sectional areas. It's probably the lowest capacitance of any of them. And I guess they make most of them with germanium because of the higher carrier mobility, which means that the holes and the free electrons can move quickly through it. So it makes a good RF detector. So what is the common use for a point contact diode?
An RF detector.
Yeah, so
An RF detector.
I heard this.
Would that be an envelope detector? And a light emitting diode. Okay. There's probably nothing nowadays that doesn't have one or more LEDs in it. It's like a regular diode. When you forward bias it, it conducts. When you reverse bias it, it doesn't. They control the color of the light by the material they use. So the forward voltage drop in an LED will be quite different. Can be 1.5, almost 2 volts in some cases for forward voltage drop. The symbol is like an LED with some arrows pointing out, showing the light emitting from the diode. Again, it's a simple P-N type junction. They're put in a clear, sometimes colored case, so that you can actually let the light out. Like I said before, all diodes actually emit some because of the energy given off when you recombine the electron in the hole. Because the hole is going down to a lower level, it's going back into the valence energy band. So that energy gets released, and some of it can produce light, some of it can knock another electron out, or some of it can create heat. So what type of bias is required from LED to emit light? What's the schematic symbol for a light emitting diode? Oh, you circle out. Okay. Oh, here's the junction temperature. That's in the beginning. How'd they get down there? All right, so you have to be careful not to exceed the forward current specification, because that causes the junction temperature to increase because it's proportional to the current. So, and they'll limit the maximum junction temperature for the devices. So when you get up to that point, it will at some point fail. Usually when you don't want it to.
Here's a question again.
Yeah. Maybe it was supposed to be at the end.
I think your answer was supposed to be back over here.
Maybe you're just giving us a preview.
Oh, that's what, yeah. The end should have taken, the first one should have been the
Some of the
last.
slides were out there.
Huh?
Takeaways. Some of the slides were on the movie.
Okay. I didn't have time to fill in the takeaway, so it's what you should have learned. So you learned it all, so. Everybody's gonna pass that part, right? So we're at 6 questions down.
That's the plan.
Yep. So before we go. And one more today.
Yeah.
If I can find. I don't know why these are taking so long to come
I
up.
wonder how many LEDs are in that screen.
Huh?
So I wonder how many LEDs are in that screen.
They're very small, but I can see them.
Bob, we gotta jump on you because remember Steven's gotta go.
All right.
We will see you next week, or I will see you next week.
Okay, and you're gonna be on Zoom?
No,
No?
I'll be on vacation.
Well, that's no excuse.
I have notes, because I'm sure that there will be downtime when they all want to do something and I'm not interested.
Okay,
I'll
well,
be texting him pop quizzes.
like I said, I'll try to get them on Zoom in the next day or two. And the charts on Dropbox.
I'll have my iPad so I can check.
And I'll send out another set of links for Dropbox and Zoom.
This is helpful because it does, it's goes over the same information that's in this book, but it's in a different, slightly different order. So what it does, it forces me to go back and forth looking at information.
Yeah, well, all his books, he tries to do the technical basic stuff before you get into the operations and rules and regulations, which makes sense to me. Not to the ARL, because they go 1, 2, 3.
All right, gentlemen, see you next Saturday.
All right.